Hi, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 49. In this lecture, we'll discuss thermodynamic cycles. This topic is covered in Chapter 22 of our textbook by Surway and Jouet. A thermodynamic cycle is a series of thermodynamic processes that returns a system to its initial state. Recall that in previous lectures, we've discussed four fundamental thermodynamic processes, namely the isochoric, isobaric, isothermal, and adiabatic processes. Those processes can be combined in sequence in such a way that a system ultimately returns to its initial state. The system that we're talking about here could be a volume of gas, for example, that is being manipulated by our thermodynamic processes. The gas starts with some initial state characterized by some initial pressure or initial volume or initial temperature. Those parameters can then change throughout the thermodynamic cycle, but ultimately those parameters must return to their initial state, to their initial values. So you can think of a thermodynamic cycle essentially as a circular or closed thermodynamic process. What's important for us is that the final pressure of the gas or the system must equal to its initial pressure, and the final volume must also equal to its initial volume. Now, the systems that we are most interested in this class are ideal gases. For an ideal gas, pressure and volume and temperature are related, and if the final pressure and the final volume are equal to their initial values, then the final temperature must also equal to the initial temperature. This is essentially dictated by the ideal gas law, which states that PV must equal to nRT. We're assuming that our system is an ideal gas and that the number of moles or the amount of gas doesn't change. Therefore, if P and V are returning to their initial values, then the temperature must return to its initial value as well. This also means that the final internal energy of the system must equal to the initial internal energy of a system for a thermodynamic cycle. This is dictated by the equipartition theorem. Recall that according to the equipartition theorem, the internal energy of a system is equal to the degrees of freedom times the number of moles times 1/2 RT. If the initial and final temperatures are equal to each other, then the initial and final energies must also be equal to each other. Most importantly, what this means is that the change in the internal energy of a system in a thermodynamic cycle must equal to 0. Since a thermodynamic cycle returns a system to its initial state, it can be repeated over and over again to perform work in a continuous manner. Any device that uses a thermodynamic cycle to perform work in a repeatable manner is referred to as a heat engine. So the importance of thermodynamic cycles lies in that heat engines can use them to perform work in a repeatable or continuous manner. There are many different kinds of heat engines depending on the thermodynamic cycle that is being used. For example, the Rankine cycle is the thermodynamic cycle that is used in the classic steam engine that might be used to power a steamboat or a locomotive. In the case of a train locomotive, the working substance or the thermodynamic system that is being manipulated is steam. So water is heated by burning coal or wood. The hot water evaporates, turning into hot steam. The hot steam then expands, pushing against the piston, and the piston in turn pushes against the wheels of a locomotive, propelling the train forward. Of course, an expanding gas eventually cools down. That allows the piston to then compress the steam back to its initial state. Once the steam returns to its initial state, the process can be repeated over and over again, performing work in a continuous manner. The Otto cycle is the thermodynamic cycle that's used in gasoline and diesel-powered internal combustion engines. The simulation here shows a 4-cylinder engine. The working substance, or the thermodynamic system that's being manipulated in this case, is a mixture of air and gasoline. The air-gasoline mixture is injected into the cylinders of the engine. A spark plug generates an electric arc, or a spark, that then ignites the gasoline. The gasoline essentially explodes, generating a large amount of heat. That heat causes the air to rapidly expand. As the air expands, it pushes on the pistons, performing work. The pistons are essentially executing simple harmonic motion that is eventually converted to the uniform circular motion of the flywheel. So the oscillatory motion of the pistons forces the flywheel to rotate. Ultimately, the flywheel is connected to the powertrain of the vehicle through a transmission system, and the powertrain is ultimately responsible for transferring this energy to the car's wheels. The Stirling cycle is used in the Stirling engine, which is a small-scale, efficient engine that is sometimes used to convert solar energy to electricity. The Carnot cycle is the most efficient thermodynamic cycle. We'll discuss the Carnot cycle in detail in a later lecture. For now, I'll just say that the Carnot cycle is the cycle that would be used in the ideal heat engine. In this lecture, we're not really interested in the details of any of these engines. We're primarily interested in establishing a framework that can be used to describe and analyze any heat engine in general. As I mentioned earlier, a thermodynamic cycle is essentially a sequence of thermodynamic processes that are performed back to back. Now, there's no limit on the number of thermodynamic processes or steps that could be involved in a cycle. However, most practical heat engines use cycles with 4 steps or 4 thermodynamic processes. These processes are best represented on a PV diagram as shown here. For most practical engines, the first step of the cycle involves the compression of a gas. The compression of the gas is shown by this curve here on the PV diagram. The compression of the gas can be done isothermally or isobarically or adiabatically. Which fundamental process is used determines the exact shape of this curve, but what's important is that the volume of the gas must be reduced to some smaller value. For example, if we're talking about the Rankine cycle used in the steam engine, then the volume of the steam must be decreased as it is compressed by the piston. The second step usually involves a transfer of heat into the gas from a hot reservoir. The hot reservoir, in the case of a steam engine, would be the burning coal. So energy is transferred from the coal into the steam. That process can be done isochorically, isothermally, or isobarically. This step is represented by this pink line on the PV diagram. The next step usually involves an expansion of the gas. The expansion of the gas is represented by this red curve. The exact shape of the curve depends on whether the expansion is performed isothermally, isobarically, or adiabatically. The fourth step in a typical thermodynamic cycle involves the transfer of heat out of the gas into a cold reservoir. In the case of the steam engine, the cold reservoir might just be the surrounding air. In the case of the Otto cycle used in the internal combustion engine, the cold reservoir might be the radiator fluid that is circulating in the system to keep the engine cool. The point is that the working substance or the thermodynamic system must lose energy to something colder than itself in order to complete the cycle. This final step can be done isochorically, isothermally, or isobarically, but of course it cannot be performed adiabatically. By definition, an adiabatic process is one in which there is no heat transfer. This final step is represented by this blue line on the PV diagram. As I mentioned earlier, we're interested in thermodynamic cycles basically because heat engines use thermodynamic cycles to perform work. So for us, it's really important to be able to calculate the exact amount of work that is performed in a specific thermodynamic cycle. Recall that in general, the work performed in a thermodynamic process is equal to the negative of the integral of pressure with respect to volume. There's a minus sign in front of this integral, which you'll have to bear in mind. The minus sign is a little strange being there, but the minus sign basically allows us to say that whenever the work is negative, the energy of the system decreases, and whenever the work is positive, the energy of the system increases. This is essentially a consequence of the first law of thermodynamics. Recall that the first law of thermodynamics states that the change in the internal energy of a system is equal to Q plus W. Q is the heat that is transferred into or out of the system. For now, let's just ignore Q. This equation then tells us that whenever W is a positive quantity, delta E is a positive quantity, which means energy is increasing. Whenever W is a negative quantity, delta E must be a negative quantity, which tells us that the energy by itself must be decreasing. So the minus sign in front of this integral allows us to have this nice interpretation for work in terms of the energy of a system. Also recall that this integral is essentially the area under the PV graph. So from your calculus class, you've learned that the integral of y versus x, for example, is simply equal to the area of a graph of y versus x. You've also probably seen that representing thermodynamic processes on a PV diagram or a PV graph is a very convenient way to visualize the process. And we're going to continue doing that quite a bit going forward. So one thing we want to remember is that the work performed is basically the area under the PV graph, with there being a single subtlety, namely that this area can be positive or negative. Essentially, pressure is always positive in thermodynamics, so whenever V final is greater than V initial, this integral by itself is a positive quantity and the minus sign in front makes the work negative. So whenever the volume of a gas is increasing, you'll have to interpret the area under the graph as negative work. On the other hand, if the gas is being compressed, in that case, V final is going to be less than V initial, so the integral is going to be a negative quantity, and the minus sign in front will make the work a positive quantity. Here's what I mean a little more specifically. Imagine we're talking about the thermodynamic cycle, and the first step in that thermodynamic cycle is represented by this line here. The integral of P with respect to V essentially gives us the area underneath this graph. So that corresponds to this blue region. Notice that we're going from a small volume to a large volume. So V final is greater than V initial, which means that the work performed in this process is negative work. So we'll have to interpret this blue region as negative work. Suppose in the second step of our thermodynamic cycle, we follow this line over here. The area under this second line is this light blue region, which also corresponds to negative work. Now we are talking about a thermodynamic cycle, so eventually we want to get back to our starting point. So let's say the third step in this thermodynamic cycle is represented by this third line near the bottom. Notice here we're going from a large volume to a small volume, which means V final is less than V initial. That means that the integral is going to be a negative number, and the minus sign in front of it means that the work is positive. So the area under this third step is essentially this orange region, which we will interpret as positive work. If we want to have a thermodynamic cycle, we have to end up with the same pressure and volume that we started with. So suppose that the fourth step is represented by this final line here, and the area under that final step is this yellow region on the graph. This also is positive work because once again, the volume is decreasing. Now, of course, what we're really interested in is the total or the net work performed in the entire cycle. So what we have to do is add these four areas together, with some of them being positive and some of them being negative. When we add these areas together, we essentially find that the net work done in the thermodynamic cycle corresponds to this purple region inside the parallelogram. So the positives and the negative works basically cancel each other out in just such a way that in the closed cyclic process, the area enclosed on the PV diagram corresponds to the net work. Now, what I've shown you here was a typical four-step thermodynamic cycle, but of course the cycle could have 3 steps, 4 steps, or 12 steps. In general, if you're interested in the net work, you'll have to calculate the work done by each step and add them all together. No matter what the exact shape of these graphs are, what we always end up with is the area inside the graph. So we'll use this idea quite a bit as we go forward. A thermodynamic cycle that encompasses a large area performs more work for us than a thermodynamic cycle that encloses a smaller area. So on the previous slide, I tried to convince you that the net work performed in a thermodynamic cycle is essentially the area inside a graph of that cycle on a PV diagram. I also told you that the work can be positive or negative, so it's important for us to be able to look at a cyclic process like the one shown here and recognize whether this W net is a positive number or a negative number. Recall that any fundamental thermodynamic process can also be reversed. In other words, it can be executed or performed in the opposite direction. So for example, if we have a thermodynamic cycle that traverses the PV diagram in the clockwise direction, we can reverse each individual step and then perform that same cycle in the opposite direction, in the counterclockwise direction. It turns out if you calculate the work performed in each individual step and you add them together, then you find that for this process on the left, where we're going in the clockwise direction, the net work is negative. But if you perform the same cycle but in the counterclockwise direction, the net work is positive. In technological applications of these ideas, when you construct a machine that uses a clockwise thermodynamic cycle, we call that machine a heat engine. But if your machine uses a counterclockwise thermodynamic cycle, we call it a heat pump. At this point, the distinction between a heat engine and a heat pump is not obvious. We'll spend the next couple of lectures discussing heat engines and heat pumps in great detail. For now, just note that heat engines perform negative net work and they follow cycles in the clockwise direction, whereas heat pumps perform positive net work and they follow cycles in the counterclockwise direction. Also note that we are talking about thermodynamic cycles, which means we must end the cycle exactly where we started it. That fact means that the change in the internal energy of the system must be zero, so the energy must be conserved. According to the first law of thermodynamics, the change in internal energy is equal to heat that is transferred in or out of the system plus the work that is performed. If the change in internal energy is zero, then Q plus W must also equal to 0. The utility of this equation is not obvious at this point. Keep it in mind, it will be an important fact for us later. It essentially tells us that if you want to construct a heat engine or a heat pump in which the net work is a large positive number, then Q net must be a very small negative number. For example, if you want the net work to be 1,000 joules, then the amount of heat that is transferred must be negative 1,000. On the other hand, if you want W net to be minus 1,000, then Q must be plus 1,000. So in constructing heat engines and heat pumps, we have to strike a balance between the amount of work that is performed and the amount of heat that is transferred. So let's end this lecture with a practice problem. A monatomic ideal gas goes through the cycle of fundamental processes shown below. Calculate the net work performed. So on the PV diagram, we see a typical four-step or four-process thermodynamic cycle. Step number 1 is represented by the blue graph. It represents a compression of the gas as its volume goes from 1 to 0.5. Step number 2 must be an isochoric process because, as you can see, the volume does not change. Step number 3 is represented by this red curve here, and step number 4 must also be an isochoric process because, once again, throughout this process, the volume does not change. Now, the net work performed in this cycle is the area inside the graph, but for an irregular shape like this, it's not so easy to figure out the area inside. So what we have to do is calculate the work for each individual process and add it all together. Now, as you can see, we're going around the cycle in a clockwise direction. So this is a heat pump. The net work must be negative, and that serves as a check on our calculations once we're done. Recall that in previous lectures, we've actually calculated the work performed in each of the four fundamental thermodynamic processes. In general, work is equal to minus the integral of P dV. In an isochoric process, the volume doesn't change, so the work is equal to 0. In an isobaric process, the work performed is equal to the negative of the initial pressure times the change in volume. The calculations for isothermal and adiabatic processes are a little more involved. However, we have found these two expressions in previous lectures for the work that is done in an isothermal process and the work that's done in an adiabatic process. So now we want to use these equations to calculate the work done in each one of these four steps, add them together to find the net work. Now, step number 1 is obviously not an isochoric process because you can see that the volume is changing from 1 to 0.5. It's also not an isobaric process because the pressure is changing from 2494 to 4988 pascals. So step number 1 must be an isothermal process or an adiabatic process. It turns out by looking at the endpoints of this process, we can determine that this must be an isothermal process. How do I know this? Well, recall that we're talking about an ideal gas, and therefore we expect the ideal gas law to be valid. In an isothermal process, the temperature does not change, and in general, in our class, the size of the sample or the number of moles of gas that we have also does not change. Here I'm representing constants or fixed quantities using dots. The gas constant, of course, is a constant, and that does not change either. If the right side of this equation does not change, then the left side of this equation must also be constant for an isothermal process. Now look at the process and calculate P initial times V initial, and what you find is that the initial pressure is 2494, and you multiply that by 1, which is the initial volume, and what we get is basically 2494. Look at the final point of the process, so this point over here, and notice that P final times V final now is equal to 4988 times 0.5, which equals exactly 2494. So what we have here is a process in which PV does not change, which means nRT does not change, which means that the first step must be an isothermal process. So now I can say that the work that is performed in step 1 can be calculated using this equation here. Plugging in the numbers, we find that the work that is performed in the first step is 1,728 joules approximately. Calculating the work performed in the second step is easy. The area under this particular graph is 0. As you can see, the volume does not change. This is an isochoric process, so we can say W2 is equal to 0. The third step can also be an adiabatic process, but if you go through the same calculations that we did earlier, comparing the initial PV to the final PV, you see that it doesn't change. Therefore, you can convince yourself that this third graph must also correspond to an isothermal process. We can again use this formula, plugging in the initial values for volume and pressure to find that the work done in the third step is minus 5,186 joules approximately. The work performed in the final step is also 0 joules because once again we have an isochoric process, and now we can add these four numbers together to find that the net work performed in this process, which is equal to the area inside the graph, is minus 3,457 joules approximately. As we expected, the network is negative because when you look at the direction of these arrows, the process is being followed in a clockwise direction. And that is the end of this lecture. Thank you for your attention.